All right, so let's start the lecture. So I just want to, for this afternoon, just cover a few topics about hierarchical solvers and iterative solvers. So, Jin-Chao covered a number of things already about iterative solvers, but I want to, it's a little bit complementary with what he talked about this morning. So okay, so you have the basic. Always go back to the basic. So you want to solve Ax equal b. So actually, this is so you will see that actually these two viewpoints both will be relevant in this discussion. So let's keep this in mind. So you have the direct methods, right? Gauss elimination and UQR factorization. So if you have access to the latest Chinese supercomputer, that still works for n equal a million apparently. But for more regular folks, difficult. And then you have these iterative methods, okay? So iterative methods are quite powerful, really. I mean, it's really hard to just rely on direct methods. At the end of the day, it comes down to iterative methods and being able to figure out, good implementation. So in particular, a good preconditioner, right? So the iterative method can be very fast. They rely on very simple operations. So primarily matrix vector products and some amount of linear algebra, but most of the cost is really, these products. So for example, if A is sparse, this is very good. But then you require this preconditioner. So the problem is the convergence of iterative methods depends on the distribution of eigenvalues. And so the first Julia script that I gave you actually will look a little bit into this with just some very simple, hands-on lab, nothing really fancy, but it's kind of interesting to look at. And in particular, the discussion is often simplified into, what's the condition number of the matrix? So if you have an ill-conditioned number, then you can expect some trouble. If the matrix is well-conditioned, then things should work well. But we'll see that actually that this is really more complicated in some situations. And in many cases, you really have to look at the precise distribution of eigenvalues. Just looking at the condition number is really sort of not sufficient to kind of understand the behavior or the convergence of the iterative methods. So we'll be able to experiment this with various matrices. So in the case of conjugate gradient, so we heard a lot about symmetric pos-definite matrices and so on this morning, and obviously this is a canonical case. So Jin-Chao mentioned that all matrices at the DOE are symmetric pos-definite. Well, perhaps not so, but it's definitely this covers a lot of applications. So in this case, actually, the convergence analysis ends up being not too complicated. I mean, so the condition number actually becomes, to a large extent, the relevant quantity to look at. So I want to, so I'll come back to this result. So this is not, here I'm just presenting the simpler result for conjugate gradient, although this can be, so here the issue is, the eigenvalues are all real and positive, so it simplifies the analysis. But you can do a similar type of analysis even for general complex eigenvalues. But here I'm just presenting the conjugate gradient result. But this result I think is very important to keep in mind, and it will help understand some of the results we'll be observing in the hands-on lab. So what this result is saying is something quite remarkable and very interesting. So if you're familiar with Krylov method and so on, you're not going to be too surprised that some polynomial is involved in this error bound. But so here's what the result is saying. So this is the error in conjugate gradient step n, the A norm. And Jin-Chao discussed, the importance of this A norm here over, the initial error. And so you look at the maximum over all eigenvalues of your matrix, so real positive, of P of lambda. And so P is a polynomial of order n. Okay, so essentially, as you keep iterating you're minimizing here over polynomials of larger and larger orders. So hence the error has to strictly decay here, because you're searching over increasingly larger space. And so P is a polynomial of degree less than n. With this constraint, very important to keep this in mind. So P of 0 is equal to 1. And so you want to minimize, essentially you want to minimize P. You want to find a polynomial that is very small over the eigenvalues of your matrix, but with this constraint that P of 0 is equal to 1. Right? This is very important. Otherwise, you can make P arbitrarily small, and this whole thing doesn't make any sense. But with this normalization here, so essentially this is just saying that the constant term in the polynomial is just 1. So it's our 1 plus constant times x and so on. So you want to minimize this. And so the question is, essentially the convergence of conjugate gradient is driven by the existence of such a, or how the existence, well, not the existence, but how good, how small you can make this. Okay, so can you find a polynomial that is small over the range of eigenvalues, and in some cases it's possible, others this is more difficult. So here are some canonical cases. Let's say that if all the eigenvalues are clustered around a few points, so okay, let's just here simplify the discussion, and let's say that all the eigenvalues, so they're real positive, and they're just clustered around 1. Okay, then I say convergence is fast. Okay, so why is that? Well, you have P of 0 is equal to 1, but you're essentially free to place the roots of P wherever you want. So obviously, if you place the root of P at some eigenvalue, this is just 0, so then everything works well. So P is only of order n, so you have at most n roots and n distinct roots. So you have fewer roots than number of eigenvalues, so you cannot make P of lambda 0 for all eigenvalues. But if they're all the eigenvalues are clustered around 1, the idea is you're going to place n roots essentially in this cluster around 1. And then if P is 0 at many points inside this cluster, you can also expect that it's going to be small at nearby eigenvalues. Okay, so now you can see that convergence is fast if eigenvalues are inside a cluster. In fact, so you can generalize this argument to if you have a few clusters, then this is going to work as well. Here's a result for the ill-conditioned case, and this is you can prove this result by essentially taking a special polynomial. So in fact, you simply use a Chebyshev polynomial. Okay, so you look at the range of eigenvalues of your matrix, lambda min, lambda max. Okay, you create a Chebyshev polynomial. So where x ranges from lambda min to lambda max, so the polynomial is bounded over that range. Then you normalize such that P of 0 is equal to 1. And then if you look at this Chebyshev polynomial over this range lambda min, lambda max, then you can come up with this bound. It's just a very simple expression actually of the Chebyshev polynomial in that interval. So also one of my favorite PhD qual exam. So okay, and so you can see that when the condition number, so first, conjugate gradient has this wonderful property that only the square root of the condition number actually appears, not the condition number itself, but just the square root. So this it could be in fact quite small, even for hard cases. But nonetheless, it's square root of k. So if k is large, this is close to 1, and this whole thing will converge rather slowly. So any comment about, actually, if you look at this result, and this result, you see that there is a contradiction, right? So what do you think is the contradiction? So here I'm saying, convergence is driven by the condition number, and that is an upper bound at least. And here I say, if the eigenvalues are clustered around a few points, then the convergence is fast. So is there sort of a paradox or some sort of, not contradiction, but, something perhaps not entirely obvious between these two statements? Well, let's say that I just pick all so I have n eigenvalues in my matrix, but let's say that they're repeated. So actually, there are only two distinct eigenvalues. Right? So if you have two distinct eigenvalues, how fast is conjugate gradient converging? So he said you want to give me the answer. So what's the value of n to reach convergence? Right, it's 2 or 2 or 3, right? I'm not sure exactly what the exact number is. But basically, yeah. So yeah, maybe just 2 actually. So you have two distinct eigenvalues. So you have quadratic polynomial with 2 roots. You can make p of lambda 0 at these 2 roots, and then at n equal 2, boom, conjugate gradient will actually exactly converge. Okay, and this is a well-known case for conjugate gradient. But you see that this is actually a little contradictory with this. Of course, this is just an upper bound, so I mean, there's no actual contradiction. But you can make these two eigenvalues. Well, you can create a matrix. You can make, let's say, the largest to be 1, the smallest to be super close to 0, and have a condition number that's very, very large. But still, you would converge in 2 steps, right? So here, for example, it's an example where distribution of eigenvalue, the condition number is not really. This is just an upper bound, right? It may or may not be sharp. So if you have sort of a continuous distribution of eigenvalues between lambda min and lambda max, and there are certain worst case scenarios and so on, then you're going to be close to this actual rate. But if things start clustering, let's say at the around lambda min and lambda max, actually you could converge quite a bit faster, even for ill-conditioned matrices. So I think this result with polynomials is very important to keep in mind. And realizing that, okay, the trick is, can you find a polynomial of order n with roots near the eigenvalues of the matrix? If yes, then you can expect convergence. If no, then you're in trouble. Okay, and so now this goes to then the topic of preconditioners, and I'll show you a few benchmarks and so on to kind of illustrate this point. But so most engineering matrices actually are not well conditioned. Actually, it's kind of interesting. If you talk to guys in machine learning and so on, they always work with like random matrices and all these sort of things, and their condition numbers are always order 1. So they're never concerned about convergence of their schemes. The iterative methods always converge. But so that's certainly in a lot of fields where you have matrices that are well conditioned, but for engineering cases, when you discretize PDEs and so on, as you increase the size of the mesh, typically you get ill condition, or at least the condition number increases. Okay, and in fact, the child this morning, made some nice points about why the condition number increases and why this is sort of a kind of an artifact of your discretization, and is not necessarily actually reflective of the continuous PD. So okay, so so you need a preconditioner, and so you can use the multi-level methods like multigrid and so on. Okay, that's great. And so, but this is going to be the topic of our hierarchical solvers. How can we design efficient preconditioners for a broad range of problems? And the effect, you have a good preconditioner if after applying the preconditioner, you get eigenvalues that fall into a few clusters. So, for example, if you look at this discussion here, when you look at convergence of iterative methods, very often you just look at the spectral radius of the iterative method. Like if you do a fixed point iteration or a classical iteration, then you want the spectral radius of your operator to be smaller than 1. But if you use conjugate gradient, GMRS, or Krylov-based methods, then you have this slightly relaxed criterion of you need simply the eigenvalues to be clustered. So here comes hierarchical solvers, and they're a little bit similar to multigrid, but they really do come from a different angle, and as a result, they do offer new opportunities. And so really hierarchical solvers bridge direct and iterative solvers. Okay, sorry, typo here. So there are close to multigrade, but at the end of the day, they are kind of different because, you know, they really rely on direct solvers, whereas in some sense, as Jinchao pointed out, you know, for multigrid methods, it's kind of more based on the idea of Gauss-Seidel and so on, and it's altogether a different idea, although there are many connections. And so the idea of hierarchical solvers is, okay, well, they are based on direct method ideas in the sense that you're going to do LU or Cholesky type factorization of your matrix, but it's an approximate factorization, and as a result, you know, you can reduce the computational cost of this direct factorization. So you're going to do actually what you're going to obtain is you start from A sparse, and you're going to obtain a Cholesky-like factorization, but all the factors are going to be sparse, right? So typically, when you start from a sparse matrix and you start factoring, you get dense matrices, or, you know, at least a lot of dense blocks, and the computational cost goes up. But here you're going to obtain a factorization where all the factors are sparse. And as a result, everything is, for example, linear scaling. So it's O of n, but, you know, you're making an error. And so, so the idea is then to use these methods really as preconditioners, just like a V-cycle, multigrid, and so on. Okay, but so these hierarchical solvers really blend ideas from direct and iterative solvers. For example, in fact, they can be also connected to incomplete LU methods. So if you're familiar with incomplete LU methods, incomplete LUs, these are methods where you do an LU factorization of your matrix, but then you drop entries that are created during the factorization, and you only keep the largest entries. Okay. So here, instead of dropping entries, we're going to use low rank approximation to essentially remove those entries. So as in ILU, you know, we maintain the sparsity of the matrix, but we have sort of a different process to get there. Okay, so, you know, this is sort of what I explained. So when you do direct methods, you know, they're very costly. So, you know, as I mentioned, the cost is n cube, so this can be, if you start from a sparse matrix, you know, initially you only manipulate non-zero entries, so the number of flops is quite small, but then you get this fill-in, so you get new non-zero entries in your matrix, and so the cost, you know, keeps going up. So at the end of the day, you know, for a sparse matrix, it is less than n cube. The precise cost depends on the sparsity pattern of your matrix, but the cost of me is greater than n. So here the idea is we're going to be able to maintain the sparsity of the matrix, but using low rank approximation instead of, for example, in ILU, where we just simply drop entries. Okay, so just sort of an outline of what exactly is this fill-in, and you know, how can you get a little bit of a better idea of what's happening during the factorization. So let's say you start from a sparse matrix, and let's say that you partition, so imagine that you're solving a PDE, and so you partition your grid into two domains. So domain one might be actually a small domain, and two might be the rest of the mesh, so, you know, however you want to partition it. So let's say that we perform, you know, a block Cholesky factorization. Okay, so this is what a block Cholesky factorization looks like. So here you have the beginning of the L factor. Okay, here the beginning of the so L transpose factor, or U factor if you want. And so in Cholesky everything is symmetric and so on. And so this is the short complement, right? So after you do a few steps of Gaussian elimination, you know, you have to update the rest of the matrix, and this is the formula for the update. So A11 is your initial sparse matrix, A22 is your initial sparse matrix, so everything is good here. But now you have these extra term, and so U. So did I show the? So actually, sorry, I realized I didn't show you the formula for A. So the formula for A was A11, A22, U, and U transpose. Okay. So sorry, I skipped a step here. So this is the, you know, so U is actually going to be a sparse matrix. This was the original entry in your matrix A here, the 2-1 block, and then U transpose is the block here, the 1-2 block in the original matrix. So since these come from the original matrix, you know, these are sparse. But then, you know, A11 is sparse. So if you take the inverse of a sparse matrix, you get something that's completely dense. Okay, so even, for example, even if A11 is a tridiagonal matrix, A11 inverse is completely dense. So say A11 is diagonal, then A11 inverse is still diagonal, but that's pretty much the only case where you don't have a dense inverse. So this guy is typically dense. So since U is sparse, you can see that actually this whole thing here is not actually dense, right? But there's going to be a lot of dense blocks, right? So it depends a little bit on this U that U is a matrix in A that connects 1 and 2, so it kind of depends exactly the nature of this interface. But typically, you're going to get a lot of dense blocks in this matrix as a result of this process here. And so this is why if you have a direct method, the cost goes up. So for example, in 2D, if you have a regular PDE with a local stencil, then the cost is n3/2, okay, instead of n cube. So you actually save quite a bit. But in 3D, the cost is n square, right? Because of this fill-in. This is with an optimal ordering of the matrix. You get n square, so it's still better than n cube, but it's quite a bit slower than n. So direct solvers, in fact, direct solvers are typically limited by memory. Actually, this is if you look at the benchmark, that was shown by Jin Shao on this new Chinese supercomputer. It was only I don't know the 3 seconds it was exactly, but the point is actually for these problems you're typically limited by memory, right? The problem is storing your matrix, right? You're going to have a lot of non-zero entries to store. So actually the flops is actually quite reasonably fast, in fact, but you have to contend with memory because of all this filling. Okay. So this is the problem that we're trying to fight. So the question is, how can we prevent the appearance of these new non-zero entries? Is there a simple way to do that? And you're going to see that with low-rank factorization, there's actually a very simple trick you can play with your matrix, which allows you to remove all these new non-zero entries. So it's very simple. So I'm just going to show you this with pictures, no equations, to give you kind of a flavor of how this works. And then, in fact, if you have some time this summer, you can go and implement this. It's actually not that difficult. It works really well. Okay, so many of the dense blocks that appear in the matrix are, in fact, low rank. So this is not always true. So in fact, the second hands-on lab will look at exactly is this low rank approximation a valid assumption, yes or no? And this sort of depends on the PD. Okay, for certain types of PD, like elliptic PDEs, everything is good. For Helmholtz, not so great. And then there are some in-between cases, like when you have convection diffusion, where you can be either low rank or high rank. Okay, so in case of elliptic PDEs, then this is always good. Okay, and so I'll talk about this assumption of well separated. But if you look at a block in the matrix, okay, if you look at the block in the matrix, well, you're going to have this is a group of rows and a group of columns. So if your problem comes from a mesh, a finite element, or something, then the rows probably are associated with a bunch of points in the mesh, spatial points, and then the columns with another group of points in the mesh. And the typical result for elliptic PDEs is that if these points are well separated, then you have a low rank interaction. So typically, if the rows and columns overlap, so let's say diagonal entries and so on, then the rank is high. But if you look at blocks that in the mesh are well separated, then in fact the rank is small. So this is the same. If you're familiar with the fast multiple method, this is the same idea, right? In the fast multiple method, you compress the far field. Okay, so for points that are well separated. So here it's the same thing where you look at for a bunch of rows in the matrix, there are points in the mesh, columns, another group of points, and if these points are well separated, then you have this low rank property. Okay, so let's look at all of this in pictures. So I like pictures and I like scripts. So like MATLAB scripts. So we're going to be using a lot of that today. So what's a low rank matrix? Okay, so you have matrix A, So low rank matrix makes, you can represent your matrix A as a product of two factors, okay, where you have a tall thin matrix and a fat matrix. And here you have R columns, R rows, okay, so R is the rank of A, well at least if you pick R to be the smallest integer for which this factorization is possible, then R is the rank of the matrix. Now in practice, this is not going to actually to be equal, okay? We're going to make an error, which depends on the rank, okay? And the low rank assumption, so we'll see what the low rank assumption looks like. So roughly speaking, we're expecting the error to decay exponentially fast with the rank, but we'll see in examples, what exactly low rank means, and it's kind of a relative concept, really. It's a question of computational cost and how fast you want your algorithm to be. So if the rank R is small, then you're going to be very fast. If the rank starts growing, then you'll get more flops in your algorithm, and the scheme will be less efficient. So this is why actually, as a result, it's not always very easy to provide theoretical bound on the cost of hierarchical solvers, because unless you can theoretically provide bounds on this rank for a given error, which is actually practically quite difficult, it's hard to derive theoretical bounds on these methods. So you can have empirical benchmarks and so on, for example, to observe that it is linear scaling order n with the size of the matrix, but proving this theoretically is a little bit more challenging. So I'm going to use a super simple tool to explain what works. So first, I want to just look at the LU factorization. Okay, so let's say you have a low rank matrix, and you want to perform an LU factorization of your matrix. So first, you probably should be concerned because if you have a low rank matrix, and if you just do a straight LU factorization, most likely you're going to encounter a zero pivot quite rapidly. But if you use full pivoting, then in fact, then you can prove that you can perform R steps of LU factorization, and you're guaranteed not to have any zero pivots. Mm-hmm. So you can successfully, carry out R steps of your LU factorization. Okay, so essentially you have to pivot your matrix so that the first R columns are linearly independent and the first R rows are linearly independent, and then you're good to go with that. Actually, it's really even simpler. It's really just the first R by R block needs to be non-singular. It's another way of looking at this. So okay, so let's say that you take so you do this pivoting business and so on, or let's say your matrix is already pivoted, so the first R by R block here is non-singular. If you do LU, then this is the beauty of, and in fact it's a well-known fact, right? There's nothing surprising. Okay, if you do your LU factorization, okay, and the matrix is exactly rank R, then when you're done with your first R steps of factorization, so you get an upper triangular matrix, except that this whole part here is just a bunch of zeros, okay? And if you only want an approximate low rank factorization, then here you're gonna have just small entries, which you can just threshold to 0. But for rank R matrix, this is exactly what you have. And so what we're after is, and this is the wonderful thing, here you start from a dense matrix n by n. Okay, you perform R row transformations, okay, from just the LU factorization, and you end up with a matrix that has only R non-zero rows, okay, and so this could be a massive number of zeros here, okay, and essentially, so the way we're going to apply this is we go through our factorization, we get a dense block in the matrix, we do our LU trick, and boom, we create a whole bunch of zero entries. So essentially, we can restore the sparsity of the matrix through this trick. And in fact, if you look at this, you will see that this is closely related to algebraic multigrid. So it's not clear right now what's the connection, but essentially, all these guys will correspond to fine unknowns, so the fine grid, and these guys will go to the coarse grid, and you solve for that at the next next grid level, so in a sort of a multi-grid fashion. But this is, you see how this is different from multicade because it's based on LU factorization, so it basically lower triangular transformations instead of Gauss-Seidel. Okay, so so now if you put, so here this was just the previous slide was the result of doing an LU transformation, so you get the upper triangular matrix with a bunch of zeros, but now if you actually form the LU factorization itself, so this is the L factor and U factor, so usually the L factor you have identity here, but since it's all a bunch of zeros here, you can also remove this identity and make it 0, so now you recognize that in principle you just have a square L and U factors, but in practice you can just keep these R columns and R rows, and so this is exactly the low rank factorization we're after. Okay, so you can just use the well-known LU factorization that we all love, and you have lots of very efficient implementation of this, and so this is just a very simple and efficient way of coming up with these low rank factorizations, and more importantly for us of introducing a whole bunch of zeros in an initially dense matrix. So now let's see. So again, this is going to be very, very schematic, just a bunch of pictures and so on. But how can we use this? So let's see. What happens when we go through a factorization in our matrix, and let's see how we can apply this LU factorization method to remove the fill-in that appears during the factorization. Okay, so the idea of the method is you perform, you do your Cholesky factorization, so you do a bunch of row and column transformations, okay, and as you go, you get some fill-in, and then you apply these additional triangular operations in order to restore the sparsity of the matrix. And you can prove that assuming this low-rank fill-in, in fact, this process completes in O of n flops. Okay, so that's the cost of the method. Okay, so let's look at first sort of a cartoonish thing, and then we'll see exactly what happens during the factorization. So let's say that, okay, this is a matrix. We have a low-rank block. So the idea is, well, we're not going to do the LU factorization here. We're just going to look at this block and say, so if you want to do an LU factorization on this block, so what's an LU factorization, right? It's just a bunch of row transformations. So we're applying a triangular matrix on the left, okay, it operates on the rows of the matrix. So you can look at these row transformations, and so you take this matrix, essentially you perform R steps of the LU factorization, okay? And then, so basically you're operating on the rows of this guy, but you might as well operate on the rows of this entire matrix, okay? So if you do this, so you apply the row transformation on the left, so here, you get a whole bunch of stuff, but, okay, now since, you do R steps of LU for this block here, then this is what you have, okay? So essentially, again, you replace this dense, green block by a block that has a lot of zeros. In fact, there's really only R rows that are non-zero here. So you're able to sparsify your matrix. So this is the idea. You start performing a few steps of Cholesky or LU factorization, and when you have a fill-in that occurs, then you use its additional row transformations to sparsify the matrix. In fact, it's kind of interesting. It depends exactly how you do it, but these row transformations actually correspond to essentially triangular matrices, but they're upper triangular. So in some sense, in LU, you're doing lower triangular. So here, now you have, in the factorization, you have a combination of lower and upper triangular matrices. So it's not, you don't end up with a classical LU factorization. You end up with just a sequence of, lower and upper factors. But, obviously, this is all good because, the key point about triangular matrices is the back substitution when you do the solve is very fast. So whether it's upper or lower triangular doesn't matter. Once you have the factorization, you have a fast solve. Okay, and so at the end of the day, you get this very amazing result, which is that this process allows factoring your sparse matrix A into a product of completely sparse matrices. Okay. In fact, if you look at all the factors that you have, and if you look at the number of non-zero entries that you have in all the factors, all taken together, you have O of n non-zero entries in all these factors, all taken together. Right? So you have a bunch of factors with O of n entries, non-zero entries, and this gives you an approximate factorization of A. So this is, whereas a straight factorization, for example, may require, so I'd have to, so typically, so hold on. Typically if you take a 3D PD with n points in your mesh, in a regular factorization, you have n 4/3 non-zero term, right? N to the power 4/3 is the number of non-zero terms you have in the traditional Cholesky, whereas here we stick to strictly O of n, and moreover, the cost of the factorization is just O of n instead of n squared. So now what's the so now I've claimed that this was very close to multigrid, and that point is probably somewhat obscure at this point. Okay, like what exactly is the connection with multigrid? In fact, it's quite close to algebraic multigrid, but still fundamentally different because it's based, like Jinsha was explaining, algebraic multigrid or multigrid is based on this sort of multi-resolution. So the idea is you always go back to the same matrix A or the same PD and so on, but you represent this matrix or this PD at different scales. Okay, so for example, if you go to the so you always have let's say Laplace, but on grids of different sizes. Whereas here this is different. The coarse grids represent the result of this sparse Cholesky factorization. So you get these coarse grids, but they do not correspond to your original PD. They correspond to different, basically a different coarse grid that results from this Cholesky factorization. So let's look at what happens. So let's say that you partition the graph. So this looks very much like well, I guess multigrid would do this a little differently, but so here, one way to represent this is to start from the domain, and then you partition your graph or your mesh into small clusters where you have O of 1 points per cluster. So I guess here the clusters are a little bigger, but you keep subdividing until you have O of 1 points per cluster, and then you start your elimination. So the idea is you're going to take one of these clusters, so let's say that guy, okay, and then you're going to do a block Cholesky factorization on that cluster, okay. So if you do a block Cholesky factorization, what happens is, so initially you have a sparse matrix and sparse graph, but then after eliminating this block here, then you're going to create a whole bunch of new non-zero entries. In fact, what happens is if you look at the boundary, so all the nodes in the other cluster that are on the boundary, then the non-zero block essentially corresponds to new non-zero entries that correspond to all pairs of points on this boundary, right? So if you represent your sparse matrix as a graph where where an edge means between 2 points means there is a non-zero entry in your matrix, then in fact here you have if you're going to get, after eliminating this cluster here, you get a fully connected graph or a clique between all points on the boundary, and this is the dense block, the fill-in that you have. And so in fact in the so this is exactly the test case we're going to be looking at in the hands-on lab with this Julia code. We're going to be eliminating this cluster and looking at the resulting interaction between two of these clusters for just a regular grid.
Are you just clustering those based on location, or is there smarter ways?
So yeah, there are different ways to cluster this. Essentially, the criterion is quite simple. It depends. Let's say if you're in the context of elliptic PDs and so on, then there's a simple interpretation. The clustering is simply based on maximizing the separation between clusters. So basically, if you eliminate this guy, you're going to create this fill-in, and you want, if you look at pairs of clusters, you want most of them to be well separated. So the criterion is something like, for a given cluster size, you want to well, something like you want to minimize the radius, or you want essentially any 2 points on the boundary to have maximum distance, right? So you want it to be close to a sphere in some sense, right? So that you have maximum distance between opposite points on the boundary. So for example, a very bad case is a cluster you had like this, right? If you eliminate this, then all the clusters on the boundary are all very close to one another, and so you're not going to get this lowering property.
Is there a particular method that you use for that?
Yeah. So well, yes, it's a very bad one. we just use a regular graph partitioner, but the problem is graph partitioners are typically designed to reduce communication. I mean, if they were optimally, when you minimize communication, in fact, this is the same criterion as if you want to minimize the surface. In fact, you also want to create clusters that are roughly isotropic. So this is in fact the same criterion. It's actually our same criterion, but it's so right now this is what we're using. But I think there's quite a bit of improvement that could be gained if we had custom partitioners that really looked at you want to do hierarchical solvers, so we want certain quality in the partitioning with certain measure of quality, and just design an algorithm just for this.
Thanks.
Yeah. Okay, so let's take an example, and I'm going to show you what happens. Again pictorially, just to see a little bit. So this is if you wanted to implement these methods, how would you do it? What would the operations look like? So let's say that you do a block elimination. So you eliminate one of these guys, that guy. So then you create all the nodes on the boundary here are going to be all connected. So you're going to have this fill-in occur, and so you want to sparsify it. And so what exactly does this mean? Okay. So essentially, let's take a cluster. So actually, this is a slightly different point of view, but this is actually the one that we need to look at. So essentially, the idea is actually not to look at I have eliminated this cluster, this fill-in. Let me compress this fill-in. It's a little bit easier to look at this problem from a slightly different perspective, which is to say, okay, let's just factor the matrix, but instead, each time we're about to factor a new block pivot, we look at the pattern of fill-in we have at that point, and then compress the fill-in. I mean, obviously, it's kind of the same point, but it's just looking at this problem in a slightly different way. So let's say that we've already eliminated a bunch of clusters. Let's say, I don't know, maybe we've eliminated some of the top ones here. Now we want to eliminate this guy. Okay. So you're going to have the original stencil right here, but then you're going to have a whole lot of fill-in corresponding to these eliminations. So maybe all these nodes here are going to be connected to a whole bunch of nodes and so on right there. Okay. So these are the dense blocks, and so the process is okay. Well, before doing the factorization, we want to remove these edges, or we want to create, we want to sparsify the matrix. Okay, so this is how really the algorithm proceeds. We let the fill-in occur in some sense, but then once we get to each time we want to factor a pivot, then we look at the fill-in and try to compress it at that point. So let's say that we have this lowering fill-in. So actually in practice, here I'm showing green for the entire matrix. We really you'd have a few dense blocks, instead. Here and here, so it would be symmetric. So let's assume we have some dense blocks here, or maybe this whole thing is just dense and low rank. So here it's sparse. The rest of the matrix might be sparse as well. And so how do we do the factorization, and how do we connect this process to multigrid? Okay, so here's what happens. Okay, so it's Cholesky. So in Cholesky, you have to do things. Well, everything is symmetric. So essentially, you're going to do row transformations. But whatever happens here, it's so you also do column transformations, but they're identical. So you only compute one half of the matrix. So you do these row and column transformations. So you get as a result, so you do this LU. You do LU here, so you sparsify your green block, okay? Sparsify your green block here. And so now you've introduced a whole bunch of new new zero entries. You specify your matrix. So it means that it's basically, if you think about this in terms of a graph, representing the sparse matrix as a graph, it means that you've removed a lot of edges from your graph. Okay, so you apply row and triangular transformations that remove edges from your graph to create all these zeros. So now, what do we do with? Well, we're still left with some non-zero entries. Okay, and we must be left with some non-zero entries because it's low rank, but the rank is not 0, right? So here you must have some rank R. So we left with some green. What should we do with this? So here, this is basically that's the idea. Okay, this is going to become the coarse grid. Okay, the unknowns we eliminate at that step are the fine grids. The unknowns that remain, these green unknowns, are the coarse grid that we're going to solve at the next step. So that is a connection with multigrid, algebraic multigrid. So let's say that we're at that step. Now just pivot everything. Okay, so now we sort of split things into fine nodes and coarse nodes. Okay, these guys are the fine nodes. So we're going to proceed and eliminate. These guys are the coarse nodes. Okay, and so the way the algorithm works is we start on the fine grid. Okay, eliminate all the fine nodes. Okay, and then we're done with that. And then we're left with a bunch of coarse nodes. Okay, so on the coarser grid, and then basically just repeat the process. But let's say that each time, for example, so these are the coarse unknowns, these are the fine unknowns. Let's say that number of coarse is equal to number of fine. Then you see that the matrix size shrinks by a factor of 2 at each step. So you quickly with 10 levels or whatnot, you can get to a very small system that can be just solved using the traditional direct method. So okay, so you swap all the coarse unknowns at the end. So the fine you keep, okay, and that's the next step in the edit factorization. Okay, so this will be next block to factor, okay, and so on. You move the coarse nodes at the end. Okay, so it's just a permutation. And you see that, for example, when you factor out the fine nodes, it's kind of interesting. What happens? Actually, the only thing that happens is the only thing that changes is the coarse interaction, right? So the sort of diagonal block for the coarse unknown is updated. But for example, the coarse and its connection with all other clusters unchanged. Okay, it's unchanged because when you factor this guy, okay, the only thing that the short complement, here it's all a bunch of zeros. Short complement is just this guy minus this times this inverse times that. So this is the only block that actually gets modified by the factorization. So it's very straightforward, and it's very straightforward, and so this is how you get this order n cost. Okay, so you keep doing your Cholesky factorization, and then you remove this fill-in through these low-rank LU operations, and then you partition to fine coarse, and then eliminate the fine. Okay, and the coarse unknowns correspond to next level in the grid. So this will be eliminated at the next round. So let me show you this. So this movie here. So this is showing. This is your original. Whoops. Sorry, I need to move my mouse here. Oh, can you stop here? So maybe here. Okay, so what we're showing is this is the graph of the matrix. You're actually not seeing the edges, but just the cluster and the different colors. This is a pictorial representation of the coarse unknown. So here you really have like R unknowns at each of these big nodes. And then you just go and factor. So these, for example, correspond to fill-in entries. You've removed all these blocks. So for example, that guy becomes connected to that guy. But they are well separated. Okay, so you do your low-rank compression, and then this is going to create the coarse grid matrix. Okay, and these gray edges are edges that correspond to, in fact, the coarse grid. So you have coarse unknowns on the coarse grid and with coarse edges. And the key thing is, if you look at the process here, you can see that each red node is only connected to surrounding neighbors, and similarly if you look at the fine clusters, they're always connected to near neighbors. In fact, you can show that you never create fill-in beyond a distance 2. Okay, so if you look, for example, distance 1 means cluster is connected to here a neighboring cluster. So we say distance is 1. So distance 2 means neighbor of neighbor. Okay, so you never go beyond that because each time you have such edges, you apply this compression idea, and so this prevents the growth of your stencil. Okay, so this is how things work. So you can see you go through animation that the stencil always stays local. Okay, you create all these orange edges, which in principle, would very quickly, everything would be all connected here. But because we compress and represent this using a coarse grid, actually so we're still left with something. We're still left with coarse grid matrix, but the stencil stays local. And so you can see how this is now similar to multigrid, but it's based on Cholesky and LU factorization, so it is different. But you start on fine grid, factor, you get a coarse grid, factor again, and so on. And if you look at the process, for example, of the solve, then the solve is very much like a V cycle, because you can have operations on the fine grid, and then like the backward solve is going from fine grid to coarse grid and so on up to the top, and then the forward solve would be going from the top. You get the solution at the top, and then you propagate down to the bottom. Okay, so it's very similar to multigrid in that fashion, but it's based on different ideas. Okay, so I guess we're getting close to the break. So I'm going to just finish up with showing you some results, and then in the second half of the talk here, we'll just look at the Julia code that I gave you and run some benchmarks to get a little bit of a better feeling of what this is all about. So I just want to show you a few results that just some things that I've gathered from my students, the different projects they're working on. So I just they had some nice results, so I sort of collected some results that I thought were interesting. So first I want to look at convergence of iterative methods. So I mentioned that for conjugate gradient, in SPD matrices, so eigenvalues are real and positive, so you have a very simple convergent behavior just based on the condition number. But for unsymmetric matrices, things are quite a bit more complicated. So the eigenvalues, let's say the matrix is real, so for each eigenvalue you have the complex conjugate, also is an eigenvalue, so that you have pairs of eigenvalues, with complex conjugate. So condition number, obviously is still important. If the condition number is bad, is very large, then the convergence will be slow. But really, coming back to this idea of polynomial, it's really the clustering of the eigenvalues that matters. And so, in fact, you can get some interesting cases, and this is something you guys will be able to play with this Julia script. So, for example, let's look at these different situations here. So this is the complex plane. And these are the eigenvalues of different matrices in the complex plane. So the 0 is here. Okay, 0, 0 is here. So let's look at this orange case here. So here all the eigenvalues are sort of clustered around 2 maybe. Yeah. So with a radius, you have a circle of radius 1. And everything is clustered around 2. So we expect, so eigenvalues are, so if you put, the roots of your polynomial around here, then P of lambda will be small over this region, and so you expect very fast convergence. In fact, this is you get super fast convergence. In like 25 iterations, you're at 10 to the minus 5. So this is great. But if you look at these results, and this is going to be very perhaps counterintuitive, or this is very different from what you have in here. So if you look at this matrix here, okay, again 0, 0 is here. So let's look at the blue case. Okay, the eigenvalues are basically on the unit circle. So I think actually they're just random angles on the unit circle. So the condition number, if you look at the lambda max over lambda min, condition number is actually just 1 here, but the convergence is very, very slow, right? In fact, if you think about the following matrix, let's say you take a matrix that takes E1 and sends it to E2, and then takes E2, sends it to E3, and then E3 to E4, and so on, En minus 1 to En, and then let's say En to E1. Okay? If you take this matrix and you look at the Krylov space that you can build, you see that you're not going to get the convergence. Indeed, cannot occur, generally speaking, until you reach n steps. Okay, because the so if you look at the Krylov subspace interpretation, you're going to see that you cannot expect any convergence. And this is essentially what's happening here. Here you have a bunch of rotations, although they happen here in different planes. So this is just a random matrix. So you have a bunch of random planes, and each eigenvalue is basically correspond to rotation in one of these planes. But because you have all these rotations and so on, actually you do not observe any convergence, although the matrix is completely well conditioned, and if you look at it, it's a totally fine matrix. But essentially convergence doesn't occur until you reach the size of the matrix. And interestingly, if you look at the green actually the condition number is worse, because smallest eigenvalue may be here, largest may be here. So actually condition number is worse, but you can see that actually it's easier to cluster here, right? Maybe you can put the roots of your polynomial here, and then you can make a polynomial rather small. So actually green is actually, well, it's still essentially very, very bad, but in fact it's slightly better than so actually here you can see the condition number is really not such a great measure. And in fact, if you look at the unit circle, now this is almost the worst case scenario, because remember P of 0 has to be 1, so you want a polynomial that's 1 here and that's small everywhere here, and so you have to put all the roots of the polynomial on the unit circle, and you see that essentially it just doesn't work, right? It's very hard to make P small everywhere on the unit circle. In fact, you basically need to put roots essentially everywhere around until you see that you get convergence. Okay, so and now a couple additional results, but so this is just things that my students are working on. So for example, in the PSAP project, we're working on this radiative transfer equation for so it's like a solar device. You have a radiation coming into a liquid with glass beads, and the sun heats up the beads to get solar energy, and so we have to solve this radiative transfer equation. So this is what the PDE looks like. So there's like convection, there's radiation, there's some source. So we're solving for this radiation intensity, and so here I just happen to have this figure here, but it's actually you don't often see this type of figure because it's actually rather expensive to produce. But let's say that you apply ILU preconditioning to this problem. It turns out that because this is the way this PD is constructed, actually ILU works quite well on this matrix. Actually, ILU is a very interesting scheme. It's I don't think there's a lot of theory regarding the convergence, at least not that I'm aware of. But there's not that much known about the convergence of ILU. So it's definitely not foolproof. You can definitely have cases where ILU doesn't work. But there are many cases where it works, and it's not actually very. I don't think people understand very well when or it works or doesn't work. But in this case, it actually works very well. So this is, for example, the original eigenvalues. So 0 is here, so you can see that this is typically a very bad case, right? Yes, eigenvalue is very close to 0. Dense distribution of eigenvalues up to here. No apparent clustering, so it's very, very bad. You apply ILU preconditioning. So actually, to assemble this matrix is kind of expensive, because the way it works is, well, at least one simple way to do it is you basically take a vector, let's say E1, 1, 0, 0, 0, and so on. You multiply by A, you do an ILU solve, and so this gives you one column in your preconditioned system. Okay, you assemble all the columns in your preconditioned system, so typically you get a dense matrix, which is the sparse matrix times the preconditioner. And then you take that preconditioned system and compute the eigenvalues. So it's kind of you really cannot do this for large systems, but here we just took a small system, and this is what you have. And so that you see that actually this is 1, 1, 0. So you have a very nice clustering around here, and so here you get very fast convergence for this problem here. And so I have a couple more results to show you. So one case that's difficult to solve are indefinite cases. So, I was asking about Helmholtz this morning. Okay, well, I don't know. Maybe solving the frequency problem is a bad way to to write down to write down the problem. Maybe you want to stick to time-dependent formulations. But okay, if you're in the frequency domain, you end up with this Helmholtz equation with the frequency and so on. So this is here solving the Helmholtz equation using an integral formulation. So I talked about sparse matrices. Actually, this leads to dense matrices, but the methods and codes are quite similar. So this is what the integral formulation looks like. So you're solving for instead of solving for a PDE. So instead of solving for the unknown everywhere in the domain, you just look at the boundary, and U is defined on the boundary of the domain. Okay, and so you have this equation that involves integral on the boundary of the domain. Where you have U here and Q is the du dn. It's the flux. So you solve this integral equation, you get U on the boundary, and then once you know U on the boundary, you can reconstruct your solution everywhere inside the domain. So these are very powerful methods because instead of solving for unknowns inside the domain, you only solve for unknowns on the boundary. So you have relatively few points. The problem is you have a dense matrix because of all these integrals. But if you use fast methods like the fast multiple method and the H solvers, then actually you can get a very fast solution. So this is the gamma function, for example, right here is the exponential ikx over x. So this is the Green's function for the 3D Helmholtz equation. Right. So the I are the incident field information, okay, pressure field, and so K is the wave number, and so this determine how oscillatory essentially your solutions are. If you look at the U on the boundary or the solution domain, it will have wavelength that are given by this wave number K here. So this is a collaboration with Toru Takahashi at Nagoya University and Peter Coulier, who's a postdoc in my group at Stanford. So we have these three problems. Head problem, so some random geometries. Horse problem here, a TV, very important problem. You're watching TV in your house. So how do the acoustic waves propagate through your house? Is it bothering your neighbors? You have to close your windows. So this is the type of problem we're solving. And actually, the story about this problem here is actually quite difficult. The geometry is actually non-trivial. There are lots of holes because of the hair. There's some holes in the geometry. And we solve for different incident fields and so on. And so here, for these problems, there are relatively few preconditioners that work well. So for example, point Jacobi is actually a very popular preconditioner for these problems. So let's look at this, the woman's head. So this is the wave number 32. So basically, choice of K and the size of the head dictates how many wavelengths you have in the through the object. Okay, and so this is the convergence. So the IFMN is basically the hierarchical solver, but it's based on the fast multiple method. So it's inverse fast multiple method, but based on hierarchical solvers. So this particular version is called IFMM, and PJ is point Jacobian. So because it's an indefinite problem with this wave number and oscillatory solutions, the convergence actually is very, very slow. Whereas with the hierarchical solvers, we get something that's very fast. So the cost of the preconditioner is actually quite high. Okay, this is the time it takes to build the preconditioner, but then you get a very fast solve. So for example, this is point Jacobi. Each iteration is very fast, but you just have a lot of them. So total time is actually quite large. Whereas with the inverse FMM, you get very small number of iterations. So each iteration is more expensive, and you need to build the preconditioner. So actually, this is preconditioning time to do iterations, so the MAD-VEC essentially. But the total time, ends up being quite a bit lower because essentially here, there's so many iterations that the cost of the DT method is very high. The cost of building the preconditioner is very small, but then you pay with a large number here. So here, you build a very high quality preconditioner that gives you a very small number of iterations, and so at the end of the day, you win. So here you have a similar benchmarks, but you vary the frequency. So you increase the frequency from low frequency to many more wavelength in the object, and this is the blue is point Jacobi. So as you increase the frequency, the problem becomes harder and harder to solve. So point Jacobi has more and more iterations. So here it kind of oscillates, but then so basically because the number of frequencies is not that high here, so it's kind of low and medium frequency. But here, as you get to higher frequencies, the number of iterations increases. Solve time, increases quite a bit. And so nice thing is with these hierarchical solvers, number of iterations actually remains very, very small. So there's still quite a bit of time to build the preconditioner. In fact, as the frequency increases, it is more expensive to build a preconditioner. So if you keep scaling to very, very high frequency problems, it will break down. But still, for this range of problems, you end up with a total time that's significantly faster than point Jacobi. And so a couple more examples. So this is a standing horse, but similar things. We sweep over frequencies here, number of iterations for point Jacobi, number of iterations for IFMM, so this is quite constant. Here actually we're relatively insensitive to increase in K, but just a very high number of iterations overall. Total time is quite large, okay? Even the MADVEX are quite expensive because there's so many of them. Whereas here, again, more time spent doing the preconditioner, but very, very few iterations. So each iteration is quite expensive, but when you add up these numbers, you still win against point Jacobi. And finally, if you're comfortable, watching your TV, you might wonder, am I bothering my neighbors or the kids sleeping upstairs? So you can run this simulation to see what happens. So this is the wave number. So low pitch, high pitch sound, and so similar results. So now actually here you have very, very strong dependence on K for this problem. Right? Number of variations for point Jacobi increases very, very fast with K, and actually so this is also hard for IFMM. Number of iterations here increases, and the cost also increases because the rank actually goes up with the frequency here. So you're not O of n for these problems, but you're still quite a bit much faster. In fact, you're almost 10 here. So if you keep scaling the frequency, it will become expensive. But compared to standard preconditioners, we're still doing much better. And so final set of results before the break. So I guess. Yang Kai didn't give any presentation, but he's the star of today. He was mentioned several times this morning, and so he's doing a fantastic postdoc with me, and so he was looking at these hierarchical solvers for indefinite problems, so solving Laplace u minus lambda u, and so if you look at multigrid, algebraic multigrid, and so on, they for any sort of reasonable value of lambda that's not tiny, essentially they will fail because they really were not built for these indefinite cases, and so we tested the hierarchical solvers, and it turns out that it works really, really well. So here we shifted the spectrum, so spectrum is shifted to the left by various amounts. So this is a small shift, this is a large shift, and so we have still very good behavior and convergence for our hierarchical solver. So in fact, the setup time here and solve time are quite reasonable. And if you change the frequency, things still work quite well. So as I said, as you get to higher and higher frequencies, things are more difficult. You need to crank up the accuracy of your solver, and so the setup time and solve time does increase, and number of iterations also tends to increase, but you still have a very efficient solver that gives you the solution in a very reasonable time here. And if you were to do a direct factorization, it would be quite a bit slower here. So here are some of the software that you can download or look at. I mean, not everything is really entirely, it's academia, so it's kind of research projects. So this here you can download from Bitbucket. It's obviously not a software that's very easy to use, but if you're interested in using it, you can talk to my student Hadi, and he can help you, use this software, such as a generic hierarchical solver for sparse matrices. And then you have the IFMM code that Peter Coulier wrote. So this one requires a fast multiple method formulation. So it's a little bit more difficult to set up because it relies on an existing fast multiple. So Peter has his own multiple method. But if you have your own FMM, then you need to couple the two codes. So that's actually not super trivial. But it's not just basically matching the interfaces and so on. Nothing too difficult. Just a little bit of development. So this is more of a research code. But if you have an FM formulation, definitely it's not that bad. So Toru, for example, worked with Peter, and within a couple of months, he had the IFMM working. And then Toru, wrote this Helmholtz solver. So he had an existing Helmholtz solver, and then coupled with Peter's IFMM solver to get this these boundary element methods working. And okay, so some references. So this is more. So the slides are online. So there's just some of the papers in my group that if you want to. So if you want to more details, so this is about this for the fast solver for sparse matrices. So fast solvers for dense matrices, and then this was a previous work on fast multifrontal solvers. So this is direct methods, how to accelerate direct methods using hierarchical matrices. So this is a little different from this one. It's based on, so this was earlier work, but still very, very relevant. Okay, so I'm going to stop here, but so the second session, we're just going to look at this code here. So again, during the break, if you want to go there, so I gave you two codes, you should be able to run that. So if you have some issues, actually, we can look it up together. Well, actually, yeah, also, I'll help you get started at the beginning of the session, after the break. Okay, so I guess I'm going to stop here. So, okay.